Yeah, so in the last couple of classes, we were talking about the CV characteristics, and then after the CV characteristics discussion, we were getting into the second order effects, and these are the list of effects that we supposed to discuss. And as I said, there are a few effects that we will be having a glimpse of it, but there are certain effects that I will go in depth, in the sense not too much of depth at the level of physics, but certainly that would help us to model the behavior. Okay, so I'll just try to model a few of the behaviors of these effects. Yeah. So today we'll just begin with this discussion. Okay, so in the last class, when I started talking about it, I said that this velocity saturation effect is an effect that happens because of the lateral electric field. Okay, so this is an electric field that is created because of the VDS. Okay, due to this electrical field between the source and the drain, there is some physical phenomena that is happening to the IDS quantity. Okay, this is what we are going to study under this velocity saturation effect. So in order to study the behavior of our IDS, when I have a lateral electric field, what I did is I took a very long channel device, and using this long channel device, I try to derive the relation of IDS. Okay, so finally what we found is that we found two different current equation, one for the linear region. Okay, we started with the expression of QCH by transit time, and that can be written as something like mu n COX W by L, and then VGS minus VT minus VDS by 2 into VDS. Okay, so this was the current equation that we derived, and in order to get the saturation current equation, what we did is that we just substituted our VDS to be exactly equal to VDS sat, and that value of VDS sat was equal to VGS minus VD. Okay, so this is more important. So what I've done is, like, I try to replace this VDS with VGS minus VT expression. So when we do so, we end up having this current equation, which I can write it as ID sat, or the current in the saturation current, as something like half mu n COX W by L into VGS minus VT the whole square. Okay, so now let us try to plot this behaviors of long channel in terms of graphs. Okay, so I just want to plot them. One versus VGS, ID versus VGS. The other one as IDS versus VDS. And as I said, this is the graph that we call it as transfer characteristic graph, because VGS would act as a kind of input voltage, whereas IDS is nothing but an output current. So it's a plot between input and output. So due to which we call this as a kind of transfer characteristic graph, whereas the graph towards the right, that is IDS versus VDS, we call this graph as an output characteristic graph. Okay, and this one is just the transfer characteristic graph. Clear? Yeah. So now I hope that you might already know these answers. So just a quick review of it. We assume that the value of IDS is completely equal to 0. Okay, till I reach the value of VGS that is equal to VT, and beyond that, what happens is that you get some sort of current. Okay, so again, you will have different sets of graphs for different values of VDS. Okay, so we'll restrict to a single value of VDS here. Okay, and this is the kind of graph. And when I look here, the particular region where our transfer would be in saturation, assuming that we have VDS that is greater than 0. Okay, so in this particular segment, we first enter into saturation and then we get into linear. Okay, so something like a kind of a linear relation will happen here, but there is certainly some sort of quadratic relation happens at this particular zone. Okay, now why does this quadratic relation happens when I try to plot IDS versus VGS? Why does this graph takes kind of quadratic nature, like a kind of parabola at this particular junction when we are in saturation regime?
Could you repeat the question?
No, when I try to plot IDS versus VGS, we know that the transistor would be in cutoff between the value of VGS when it is equal to 0 to VT, right? And after then, it gets into saturation regime. Maybe probably this graph might not tell you exactly why we are in saturation, but I think we know that whenever the value of VDS is greater than VGS minus VT, then this is the condition for saturation. Okay, so let us assume that our value of VDS that I've plotted is greater than 0. So which means that we have a positive value for our VDS. So in that case, the moment I cross this VT, the value of VGS minus VT would be much smaller than the value of VDS that I have, due to which from cutoff, we will be entering into saturation regime. And after a while, we'll be at the edge of the saturation, and then we will move on to linear region. Okay. So for an NMOS device, I think these equations we have already seen. So we assume that the value of IDS is equal to 0 for transistor that is in cutoff, and when the value of IDS is not equal to 0, then there can be two possible regions, and the possibility of either of these two regions depends on the value of VDS and VGS, right? So if I say I'm in linear region, the relation between the VDS and VGS can be returned something like this. Okay, when the value of VDS is smaller than the value of VGS minus VT, then we will be in the linear region. Clear? But when I say that I'm in the saturation regime, then the value of VDS supposed to be greater than or equal to VGS minus VT. Correct? So now, the moment I cross this particular voltage, I have some sort of positive value of VGS minus VT, okay? Because this is my VGS axis. And when I subtract the value of VT, there will be a very small amount of voltage that I will have across VGS minus VT term, okay? And that value, when I compare with respect to VDS, it is quite smaller, due to which I'm satisfying the saturation region condition, okay? So from cutoff, we are entering into saturation regime first, and then once I increase the value of VGS, for a fixed value of VDS I'm talking, okay? So as I keep increasing the value of VGS, what happens to the VGS minus VT term? That keeps rising, and momentarily we just move from this saturation regime to linear regime once I have a huge value of VGS minus VT, which is greater than the value of VDS. Okay, so this is how they travel. So even though if you're not comfortable with this way of writing, I will talk about the same concept when we talk about DC characteristics of CMOS inverter. Okay, but the only thing that I want to emphasize here is that there is a kind of quadratic graph between the ID and VGS. When I try to plot, there is a kind of curvature that you could see. And this curvature represents a quadratic relation between the ID and VGS. So why does this quadratic relation appears? Due to what?
Term in the ID set.
Yeah. Yeah, there is a square. Yeah, exactly. So there is a square term that is sitting in this IDS SAT expression, okay? And due to which, even for a small increment in the value of VGS, the current is actually stepping by a factor of square, okay? And due to which there is a quadratic relation. And after then, you would see some sort of linear relation between the ID and VGS, okay? So this is the nominal graph for a long channel device, okay? Whatever I'm plotting is only for long channel device. I've still not yet gone to the velocity saturation effect, okay? And now we'll just get into the other graph where I want to plot ID versus VDS, okay? Now again, we know that there is a kind of no current when the value of VGS is less than VT, okay? But I would have certainly an amount of current for the value of VGS that is greater than VT, okay? So I'll just mark it as VGS1, and the next VGS2 will have a higher value. Okay, so each of these VGS are being incremented at an equal step. Okay, so what does it mean is that if I have, say for example, 1 volt, the VGS2 would be like 2 volt, the VGS3 will be like 3 volt, and VGS4 would be like 4 volt. Okay, so the difference between the neighboring voltages is all 1 volt. When I do so, you could see that the currents were expanding is not equal. Okay, it is not exactly incremented in the same equal step heights. Okay, the height difference between these two currents and the height difference between these two currents are different. Okay, and this again is purely because of this square relation that I have. Okay, because of any equal increment in the value of VGS, the current is being incremented by the square term, and due to which we would see some sort of unequal height differences in the value of IDS versus VDS graphs. Okay, hope that it is clear. Because these are the graphs that will help us to see how does velocization impacts our CARA. Okay, this is what the current discussion is all about. So now let us talk about short channel device. So when I say short channel device, we are talking about a channel length that is less than 1 micrometer. Under this condition, our relation that I am trying to plot would be different. Now, what I mean by velocity saturation is that when I try to plot electric field, that is the lateral electric field versus the drift velocity. Okay, We know that there exists a relation which is given by the classical physics that the drift velocity is given by mu times that of the electric field. Okay, we know that the electric field can be returned, or the lateral electric field can be returned as Vds divided by the channel length. And the moment I reduce the channel length, say for example like 180 nanometer, okay, what happens is that even for small values of Vds that I have, the electric field will certainly goes to a very, very high value. Okay, and due to which these electrons or the carriers, the charge carriers, attains a saturation velocity. Okay, and it never follows this expression. Okay, so what I'm trying to mean is that during the small values of electric field, the relation is generally followed or given by this particular expression. Okay, but after attaining a particular electric field, which we call it as critical electric field EC, the velocity of the carriers becomes constant and it attains a saturated velocity. Clear? I guess this graph we have discussed in the last class as well. Okay. Now clearly, this particular carrier is not reflected by this classical physics equation. So we have to modify this drift velocity expression in order to fit this particular carrier that the real device actually shows the behavior. Okay. So in order to reflect this behavior, I'm just going to slightly modify our drift velocity expression. Okay. So which is given as Vds is equal to mu times that of the electric field divided by 1 plus by EC. Okay. So classically what we had was just the drift velocity was equal to mu times that of EL. But now in order to accommodate this particular carrier, we have remodified this drift velocity expression to something that looks like this. Okay. Now there are two things that we need to observe here, which means that for electric field, that EL, that is far, far lower than the value of this critical electric field. What happens to the ratio when the lateral electric field is much smaller than the critical electric field? How I can approximate this drift velocity term? It would be still equal to?
CL.
Mu into EL.
Yeah. So this would be still following the classical physics. Okay. But the moment I'm trying to get closer and closer, say for example, for the electric field that is exactly equal to the critical electric field, what happens is that this drift velocity will become Vsat. And what is the value of this Vsat? When I try to plug in where E equal to EC, then it becomes something like this. Okay, our velocity saturation is given by this particular expression, and this expression is valid even for electric field that is greater than this critical electric field. It stays constant. Okay, and that constant value is evaluated based on this substitution. Okay, and we are keeping this as a kind of EC, and what we are plotting is with respect to EL. Okay, so any further increase in the value of this lateral electric field, this quantity will be a kind of constant term. Okay,
I have a doubt.
Yeah, sure, you can ask.
Sir, like if you increase EL, then won't EL by EC be more than 1?
Yeah, the drift velocity is actually being remapped into this expression. Okay, so we will not be utilizing this expression. This is for the case when I am having an electric field that is less than the critical electric field. Okay, so there are two different equations. Okay, and this expression is valid only when I'm working for an electric field that is less than the critical electric field. But according to the graph, this drift velocity would be equated to Vsat when I have electric field that is greater than the critical electric field.
Oh, okay,
so
sir.
These are the two different equations. Okay.
Okay, sir.
Yeah. Now let us try to evaluate the current in the linear region. Okay. Now, as I said, the current equation, as we did for the long channel, the current equation can be written as the channel charge divided by the transit time. End up having something like mu times 1 plus our lateral electric field divided by EC. Okay, so you could clearly see that there is this particular term is happening just because of this particular substitution. So the T can be written as drift velocity divided by the length of the channel. Okay, and then once you keep substituting the QCH, which I told the value of this QCH was written as okay, this VD which was our drift velocity, can be represented by this expression, which is mu times EL divided by 1 plus EL times that of EC. Okay, so I'm just trying to substitute each of these quantities here. Okay, did I write this properly? No, this is yeah. So now that you just plug in the value of this VD that we had over here, because we are in linear region. Okay, so in the linear region, the value of VDS is small. Okay, and due to which I'm just using this particular expression rather than using this expression. Okay, so hope you're clear. So I'm just substituting this equation just because the VDS value is small, due to which the lateral electric field is lesser than the critical electric field, and I'm using this VD expression to substitute over here. So once you substitute, you end up having some sort of beautiful expression where mu would be there, and there is also a critical electric field that comes here. Okay, and you have this entire equation, which is the QCH expression. The blue one is basically due to the expression of QCH, and then so one thing that I can write is like EL can also be written as VDS by L, channel length. Okay, so we will hold this as well, and due to which I'm going to substitute wherever I have this EL. This is again EL, sorry. Yeah. So where I have this EL, I'm just going to utilize this expression. So when you do so, okay, so this VDS expression is coming out of this EL term that is sitting at the top. Okay, yeah. So hope that it is clear. So once I substitute all of these things, this is the expression I have as a kind of current equation. Now I'm just going to introduce one particular term, which is known as kappa. Okay, so I'm just going to rewrite this equation that I've written here, equation number 1, in terms of kappa of something. Okay, so I'm just going to write it as kappa of VDS into the normal equation, which is mu times COX W by L, VGS minus VT minus VDS by 2 into VDS. Okay, so now when I look for the expression, what is this kappa expression? You could see just by making a comparison between the equation number 1 and 2, you could say that this kappa of VDS is nothing but it's 1 upon 1 plus VDS by EC times L. Okay, now one can also write the product of EC into L as something known as critical voltage.
Sir, in the previous expression, like, can you just like scroll a little upwards?
One, okay.
There actually EL, when we substitute VDS by L,
yeah,
then the W into L becomes W, but then like, how come W by
actually
L?
there is one more T that is sitting here, right?
Okay,
so this T has something like L by VD. Okay, so already there was one L that is coming out here because there is a cancellation. So we have two L's at the bottom. Okay, one of the L will get cancelled with this L, and one more L comes from the EL term.
Yes, sir.
Okay, yeah. So now let us talk about this kappa of VDS. Okay, this kappa of VDS has a special meaning. So it measures the degree of velocity saturation. Okay, now whenever we are dealing with something like long channel device, so when I say long channel device, we are talking about the length of the channel that is much greater than 1 micrometer, or whenever the value of VDS is small, okay, 0.1, 0.2, or 0.3. Okay, so when the value of VDS is small, what happens to this kappa of VDS? Okay, we'll talk about both these quantities. Okay, so I'm taking two cases. The first case is either I'm having a very long channel, or either I'm having a very small value of VDS. What happens to this kappa? What does this kappa value ends up? What happens to this ratio? When the value of VDS is small, what happens to this ratio of VDS by EL? Say, for example, when VDS is equal to 0, what happens? This quantity becomes 0, and due to which the kappa would end up having a value that is equal to 1, right? So whenever we are dealing with a small value of VDS, we can assume that the kappa is equal to 1, okay? Which means that this current equation is as similar as that of the long channel current equation. Am I right? This is the linear region current equation. And when I deal with small value of VDS, I'm ending up having the current equation that is similar to our long channel linear current equation. And also, when I go for a channel length that is greater than 1 micrometer, what happens to this quantity, that is VDS by EC times L? Again, this quantity will become small, okay, which is like closer to the value of 0. Again, under that condition also, the kappa of V, anything like kappa of VDS or kappa of just V, okay, would then be equal to 1. Okay, so under either of these two conditions, the kappa takes up a value of 1. Clear? But what happens on the other hand, that is whenever we deal with a shorter channel, that is for length that is less than 1 micrometer, okay, or when the value of VDS is large. Under these conditions, what value this kappa would take then? Will it be higher than the value of 1, or it will be less than the value of 1? You want me to show the expression of kappa? Kappa is expressed something like this.
Less than 1, so less than 1.
Yeah. So whenever we have a short channel or whenever we have a large value of VDS in a short channel, okay, so rather than writing it as R, I would write it as AND, okay. So this is a better quantity, okay. And rather than writing this kappa something like this, okay, I want to generalize this kappa term something like just kappa of V. How do I express this kappa of V? I'm just writing it as potential difference across any two terminal. It can be either across VGS or it can be across VDS. So I want to generalize this kappa term in terms of just V rather than specific about VDS. How do I express this kappa of V? So it is again taken from this expression. Just replace this VDS just with V, right? So when I do so, I would end up having an expression which is written as 1 divided by 1 plus V divided by VC. If you are more comfortable with writing in terms of critical electric field, you can rewrite this expression again as EC times that of L. Okay, so either of these two forms are conveying the same thing. Clear? Yeah. I'll tell you the reason why I'm writing as kappa of V rather than kappa of VDS when we move on to saturation regime. Okay. So now let us look for the current equation in the saturation regime for a short channel device. But here, before I do the derivation, I just want to provide you some sort of note, okay? So in this case, I'm not going to assume that the value of VDS sat is equal to VGS minus VT, okay? So what I'm trying to say is that whenever the transistor is in saturation regime, the value of VDS is written as VDS sat. But that value of VDS sat need not to be equal to VGS minus VT as we had it for the long channel device. Clear? So based on this, I want to rewrite it. Hope you're clear, okay? So because it doesn't follow the same rule as we had before, I'm going to express the saturation current by two different ways. And then I'm going to merge both these expressions in order to get the final conclusion out of the expression. Clear? So because the transistor gets into saturation regime, the moment the value of VDS is equal to VDS sat, I want to rewrite the current equation in the saturation regime just by substituting VDS equal to VDS sat. But this VDS sat need not to be equal to VGS minus VT. Okay. Later I will prove that they are not equal. But as of now, this need not to be equal to VGS minus VT. We'll hold this as just VDS sat. So wherever I had my VDS, I'm going to rewrite them with VDS sat, okay, and then it followed by mu CYX W by L, and then we had VGS minus VT, and then we had something like VDS divided by 2, so that VDS has to be replaced by VDS sat by 2 into VDS sat. So this is one expression, okay, and there is also one more expression which we can derive just by making use of the current equation that however we did for our linear region. How I can express this current equation in terms of charges? It is written as QCH divided by the transit time, right? Anyhow, the QCH expression remains the same, doesn't matter, okay? So it can be written as something like, okay, so this expression remains the same, okay? But what happens for the transit time is different, okay? This transit time is right now can be expressed in terms of drift velocity. But this drift velocity in the saturation regime is replaced with saturation velocity, okay? So I've replaced this VD with saturation velocity, Okay, so I'm just going to substitute each of these quantities to build up this expression. Clear? So I would end up having an IDS sat to be equal to saturation velocity times COX and then the width, and there is no L term here because one of the L gets cancelled with this L, okay, due to which there is no L term that is sitting here, and the remaining term of VGS minus VT and VDS sat by 2 would appear here. Okay, so I have two different current expressions that conveys the same current equation that exists for a transistor in the saturation regime. Okay, so now I'm going to utilize both these expressions. Like maybe I will write this as A and this one as B. Okay, I'm going to utilize both these expressions in order to derive the total saturation current equation. So in order to write this, I'm going to substitute two things. That is the kappa of Vds sat, which we had in our equation number A. So this term would be replaced with our known expression, which is written as 1 plus Vds sat by Vc. Okay, and I'm also going to rewrite this V sat. Okay, so if you want how to get this V sat, I'll first express this EC. We know that this EC, based on the continuity equation, it can be written as something like this. So it's based on the expression that we derived earlier. Okay, so if you are following it, I think there won't be any doubt within you. Okay, yeah. So this expression I have utilized. Clear? So V sat equals to mu times EC divided by 2, and that expression is what is being rewritten, something like this. Okay, so again, this EC can be written in terms of critical voltage, right? So VC by EL, because over the other side also I have this VC, so due to which I'm just taking few things in common. So whichever things that I can cancel out, I can just cancel here. So due to which I have this VSAT expressed in terms of VC. Clear? So I have got two expressions which I'm going to substitute in both these equation number A as well as equation number B. Clear? So once you have both these expressions, you could see that there are few terms. There is a kappa of VDS term, and there is also VSAT term, or the velocity saturation term. So for both these expressions, I want to rewrite them in terms of VC. Okay, and those expressions for kappa of VSAT in terms of VC and the VSAT in terms of VC is being written here. So now the only thing that I have to do is that, since because both expression A as well as expression B are conveying the same current equation, I can equate both these equations. So now that I'm just going to substitute each of these quantities, and let me try to first express them, and later I'll replace this VSAT. Maybe I'm just equating B, that is equal to A. Okay. Okay, so whichever the terms that are common, I can actually cancel them. Yeah, I think there is something that yeah. So this is supposed to be equal to VGS minus VT minus VD sat. Okay, so this is something that I forgot to mention here. Okay, so in the previous case, I think in the long channel structure, we were directly using this minus VDS by 2. Okay, but in the case of saturation regime, the channel is tapered. Okay, so due to which I'm just using only VDS sat here. Okay, there is no half factor that is sitting here. Clear? So sorry for not informing this earlier. Okay, the reason behind this substitution is just because the channel is tapered when we are in the saturation regime, and due to which this VDS by 2 is being rewritten as just VDS sat. Clear? And substitute this guy VSAT, which is VC by 2L, and we have something like VGS minus VT, VDS sat, and this kappa of VDS can be written as something like 1 plus VDS sat by VC, and there is also mu by L term that is sitting here, and then VGS minus VT minus VDS sat into VDS sat. Okay, so again, there are few common terms which we can cancel, namely the mobility and the length can be cancelled. Okay, so again, this VCs can be cancelled from here to here. And the only thing that we need to do is just some sort of cross multiplication of these two terms. So okay, so there is quadratic term which we can actually cancel on both the sides. Okay, so there is no quadratic relation, and we certainly have to rearrange this expression. Yeah, so certainly there is one particular term, and this term VGS minus VT times VDS can actually get merged with this expression on towards the left side. So you would have VGS minus VT VDS sat. Yeah, so I'm just going to take off this VDS sat in common. Now, I just want to look into this expression of VDS sat. So this VDS sat is actually proportional to VGS minus VT, but there is a factor that sits between the VD sat and the VGS minus VT. And what is this factor? How I can rewrite this factor? This factor is almost similar to the expression of this kappa that we derived earlier, right? Because the kappa of V can be written, where is that kappa of V? Yeah, so kappa of V has a form that is written as 1 divided by 1 plus V times that of the critical voltage. Okay, so when I look back into this expression that we derived here, you could see it is 1 upon 1 plus some voltage. That is, as a whole, it is VGS minus VT voltage divided by the critical voltage. So I can rewrite this expression that I have marked with orange as something like kappa of VGS minus VT into VGS minus VT. Okay, so certainly we know that this kappa will take up a value that is equal to 1 whenever we deal with. So when does this kappa term will take up a value of 1?
Long channel.
Yeah, so whenever we deal with long channel device, okay, or whenever the value of VDS is small. But what happens when I have VDS that is large? Okay, VDS that is large, as well as the length of the channel is less than 1 micrometer. Okay, so in that case, we know that this kappa will take up a value that is smaller than the value of 1. So what does it implies to this equation? Which means that my device will enter into saturation well before the VDS reaches VGS minus VT. So in the previous case, yeah, so for a longer channel device, the device was entering into saturation when the value of VDS is exactly equal to VGS minus VT. Okay, so this is for the case of a long channel. Okay, but in our case, what happens is that I'm entering into the saturation regime well before reaching the value of VGS minus VT. At this point itself, I'm entering into saturation and I'm marking this voltage as VD sat, and that VD sat can be written as kappa of VGS minus VT into VGS minus Vt. And we know that this kappa value will be small, right? So due to which I'll be entering into saturation regime before the value of Vds is equal to Vgs minus Vt. Okay, and due to which the short channel transistor has extended saturation regime. So what do we mean by this extended saturation regime? You see, in the long channel device, the saturation regime falls right from this value of VDS all the way through this. Okay, when I take a short channel, the saturation regime is much wider for a short channel device. Okay, so this is one of the physical phenomena that you can observe when you try to plot ID versus VDS. Okay, apart from this, there is also one more important factor that I want to bring out. Okay, let us look for the expression B. So when I look carefully, you could see that the value of this ID sat is proportional to VGS minus VT. Okay, either you look into the expression A or you look into the expression B, you could see that they are proportional to VGS minus VT. So now for a short channel device, let me pick this graphs that I have plotted earlier. So whenever I deal with short channel device, okay, let me pick a green one. What happens is that since the saturation current is proportional to VGS minus VT, how do I modify this graph? What modification do I need to have for this particular graph? Will I be still following this kind of graph, or will there be any differences in the graph? Apart from the device getting into saturation much earlier, will there be any other impact that I can impose on this particular graph?
We'll have equal widths between the curves.
Yes, true. Yeah, exactly. So what happens is that we'll have equal widths. So this is the kind of phenomena that we would end up having once we have a velocity saturation impact. Okay, so in a way, the current that I would get is also small. Why? Again, I will look back into our current equation. That is equation number A. So since the value of kappa takes up a value that is less than 1, the current that I would get out of the device will be small. Okay, and the same has been reflected even in this graph. When I go for equal widths, the current that I would get is small compared to the current that I was getting earlier for the same value of VGS. Okay, so there are 2-3 factors that we can see here. The first factor is the device enters into saturation much earlier. Okay, the second one, the IDS is linearly equal to VGS minus VT, and due to which I would end up having equal widths of ID sat, okay, for equal widths of VGS minus VT values, okay, or VGS values, or equal widths of VGS values. Clear? So this is the second thing that I can see. And also the current that I would get, the ID sat would be small for short channel device. Okay, so these are the 3 physical phenomena that I can observe. Okay, so now there is one last thing that I want to show here. We have plotted ID versus VDS graph. How about ID versus VGS graph? Any idea? Let me use the same graph that I plotted earlier. Yeah, how does this graph would change? Where is my saturation regime?
So even saturation would be linear instead of quadratic.
Yes. So instead of quadratic, what happens is that it will be a kind of linear. Okay, but at small values of VGS minus VT, it will be still quadratic. Okay, because the current IDS has an expression kappa of VGS minus VT. Okay, so when this value of VGS minus VT is small, what does it mean? The kappa will take up a value of 1. When I try to plot, this small portion will reflect a quadratic relation, but once I cross a particular value, it becomes a kind of straight line, like a kind of linear graph. Okay, it becomes something like a straight line. even in the saturation regime, it becomes a linear relation between VGS and ID. Clear? There won't be any curvature here. But initially, there will be a small curvature just because the kappa would take up the value of 1 when the value of VGS minus VT is small. Clear? But otherwise, it takes up a linear relation. Clear? And then you end up having a very less current after this. Okay. So these are the pictures that I've drawn, which I know that it is not that great. So I'll show you the pictures that are taken from the textbook. Okay. Yeah. So this is the kind of Cara for a long channel towards the left side, and this is the Cara that I would get for a short channel of equal widths, and also the device is entering into saturation much earlier. Clear? And this is the quadratic relation that I have for a long channel, and this is a kind of linear relation that I have for the short channel device. Okay. So hope that you have understood how does the velocity saturation impacts our ID characteristics as a whole. Okay. So in the next class, we will discuss about the mobility degradation, which we will not discuss too much. We'll just tell what does this mobility degradation means and how does it impacts our current. That's it. Okay. We will not go into expressions or derivations or something like that. We'll just look into it, and then we'll just move on to the further on ideal effects. Yeah. So let me stop here.